Hello students, in this video we'll discuss the orthogonal complement of a subspace of a vector space. We'll do this in Euclidean spaces for simplicity. Let's let U be a subspace of Rn, then define U perp to be the set of all vectors V such that V dot U is equal to 0 for all U in U. Okay? In other words, U perp is all the vectors that are perpendicular to everything in U. Okay? Then the first claim, here's our first proposition, so proposition number 1, is that U perp is a subspace of Rn. Okay? And the proof of that is simple, right? The proof is just as follows, right? So proof is just two lines. So if U is in U, for any U in U, and V1, V2 are in U perp, then U dot V1 is equal to 0, and that's also equal to U dot V2. So in particular, that says that U dot V1 plus V2 is equal to 0. And analogously, U dot lambda V1 is lambda U dot V1, and that's equal to 0. So that proves that it's a subspace, okay? Moreover, we know that I can add these two subspaces together in a direct fashion. So, moreover, note, so the next proposition is also simple. Proposition U intersect U perp is just empty. There's only the 0 vector in there. Okay, and here's the proof of this fact. So how does the proof of this fact go? Proof. Let's let U be in U and U perp. So U is perpendicular to U, which says that U dot U is equal to 0, which forces U to be 0. So the only thing in U and U perp is the 0 vector itself, which allows me to decompose Euclidean space for any subspace into U direct sum U perp, right? So in other words, if we let, so now here's the next proposition of these things. So proposition Rn, or your vector space in general, this is true in general, is U direct sum U perp, right? And the proof is as follows. We can let phi 1 through phi k be an orthonormal basis of U, which is possible by Gram-Schmidt. Then extend this to be a basis of Rn, then extend to a basis of Rn. By doing this, by doing phi k plus 1, phi n. And I'm going to do this in such a way that they're perpendicular to each other, right? So in other words, these things are going to be a basis of U, and these will be a basis of U perpendicular, right? So in other words, Rn, so V in Rn implies what? V in Rn implies that V is going to be V dot phi 1 plus V phi k dot V phi k plus the other terms over here, V dot phi k plus 1 all the way down to V phi n. Okay, great. And so now I'm in a position to define the orthogonal projection, right? So what we can say now is we can say the projection, define projection onto U, onto the subspace U of a vector V to be what? To be V dot phi 1 plus all the way down to V dot phi k. Okay? And now I'm going to build some shorthand for this. Let's just call this thing over here. Let's call this exactly just P projection sub U. And this is actually going to be a projection operator, right? Because if I do this projection operator twice, what's going to happen, right? So let's see what happens over here. So if I do this projection operator twice, projection onto U of projection onto U of a vector V, what will that give us? That's going to give us over here P of what? Pu of V dot phi 1 plus all the way down to V dot phi k, like that. And now what's this going to do? Let's call this whole thing, what we're going to do over here is we're going to take this whole thing over here, and we're going to dot it with V1. If we dot this whole thing over here with V1, all that's going to pop out is going to be this thing over here. So this is going to be V dot phi 1 in the direction of phi 1. Okay, that's great. If I dot this whole expression in here with the V phi 2, so everything in this expression, if I hit it with phi 2, everything but phi 2 will cancel out over here. I'll be left with what? V dot phi 2 in the direction of phi 2, all the way down to the last thing. The same reasoning applies that this is going to be V dot phi k in the direction of phi k, which shows that P squared is what? That P squared is equal to P. So this tells me that P squared U is equal to PU. And this is exactly a projection operator. So in other words, this PU is a projection. PU is an orthogonal projection. And we'll study more properties of this orthogonal projection in further videos, because it will help us determine when subspaces are perpendicular to each other, develop decompositions, and it will also help us to understand the adjoint operator and the relationship between the null space of the adjoint and the range of the operator, and vice versa, and the range of the operator and the range of the adjoint, and all of the connections between null space and range between the operator and the adjoint in further videos. Thank you very much.